Hello, engineering students. This is Mr. Olivier again, and I'm going to go through a second example now with the Mr. Lego Man. So, this is example 2, Mr. Lego Man beam. So, let's have a look at the question. So, Mr. Good and Mr. Evil. Okay, so we got a white guy and a dark guy. One guy looks like a bit of Darth Vader going there. So Mr. Good and Mr. Evil stand on a beam at different places. Mr. Good is standing 1 meter from the pinned end. Obviously, from what we can see here, the left hand support is a fixed beam. Sorry, a fixed support. He's 1 meter from the pinned end and he's exerted a force of 20 kilonewtons. Okay. While Mr. Evil stands a further 2 meters along with a force of 30 kilonewtons. The beam is 4 meters long. Calculate the reactional forces at each end using a free body diagram as well. So, first thing we do, number 1, we redraw the beam. So, we know that there is a fixed or pinned end and there is a roller support. First thing we know about that is that on this side, the reaction that we'll find on the left hand side is that there will be 2 forces that this support will be supporting this beam with. It'll be a vertical force. We're going to call that force left vertical, and it's going to have and I'll make it positive, and I'll make it positive. There's going to be a force left horizontal. So there's going to be 2 forces there. The roller support, the right hand side, the reaction in the right hand side is going to be, because it's a roller support, it's only going to be a vertical force. So there's force right vertical. There then are 2 forces. Mr. Good on the left, that is 20 kilonewtons, and he is 1 meter. Let's see, the same as there. And Mr. Evil is 2 meters from him. The entire beam, the length of the beam is 4 meters. So we know from there to there, it is 4 meters. Therefore, pretty simply, the leftover difference between Mr. Evil, 30 kilonewtons, and Mr. Good being 20 kilonewtons, 1 meter, 2 meters, 4 minus 3 is 1 meters. So I have redrawn it. I've checked that all the units are in kilonewtons or in whatever consistent unit pattern they are. And my assumptions are going to be, it has not been told to me otherwise that this beam is in equilibrium or not. Therefore, I assume it is in equilibrium. Assume the beam is in equilibrium, and therefore the sum of all the moments around this beam will equal 0. And as I did before, I really just say, okay, therefore the sum of all my counterclockwise moments will equal the sum of all my clockwise moments. Another way to say that is that sum of my clockwise moments, because I take this to the other side, it becomes minus the sum of my, I made a mistake there, clockwise moments. Pretty simply, all my clockwise forces will be positive, and all my anti-clockwise, all my counterclockwise moments will be negative. The same for my plus and minus. Plus, plus, minus, minus. All my forces vertical, up will be positive, down will be negative, and all my forces horizontal. And this is where I stated here my the sum of my forces will equal 0. That means all the forces downwards will equal all the forces upwards. And then what I do there is I take this over to the other side, plus forces upwards minus forces downwards. And that's how I get my drawing like that. So my assumptions are done if my beam is in equilibrium. So let's get straight to number 2. Number 2 is we want to solve either the reactional forces around this roller support, which is effectively we want to find that, and then we want to then try to find the forces around the pinned one, and that's going to be the forces vertical, and because it's a pinned, the forces horizontal. So straight away I'm going to take a moment around RL. Take moments around RL to find RR, or in this case the forces around R that are vertical, because it's a roller support is only going to be vertical. So again I go, the sum of my moments around RL will equal 0, okay, which then also equals plus all my clockwise moments minus my counterclockwise moments. See, like I've done here, clockwise moments minus my counterclockwise moments. Remember the diagram and the visual aspect is pretty easy to remember. Moments are force times distance, so I go plus force times distance minus counterclockwise force times distance. So what I do now is I have to look to see how many forces are pivoting around this, causing this beam. If this was a seesaw and I'm doing my moments around that, what forces are going to cause this beam to go clockwise? So the first one is going to be the 20 kilonewtons. That is 1 meters from this point. So I make my big square brackets and I go, what is the force? It's 20. Mr. Good is 20 kilonewtons times it's 1 meters from there, 1 meter. But I've also got another force here. So I add that force, which is Mr. Evil, kilonewtons times how far is Mr. Evil standing? What that force, that 30 kilonewtons, it is 1, 2, 3. 3 meters from there. So it's times 3 meters. So those are all my clockwise. It's positive. I know it's positive because it's all under there. That's my clockwise motion. And then now my counterclockwise or my anti-clockwise. I got no other forces pushing upwards to make my beam pivot in this direction, the anti-clockwise motion, except for that support which is supporting it. And I'm going to assume it is positive because upwards is positive. So it's force times distance. I don't know what the force is, but I'm going to call it force R vertical times how far is it from there is actually the length of the beam, 4 meters. And now I just extract it out to make it make sense. So pretty simply, (20 times 1 is 20 kilonewtons per meter, plus 30 times 3 is 90 kilonewtons per meter. There's all my clockwise motions, that one and that one, minus 4 force of the right hand side vertical, and I've still got it in meters. Okay, so simpler way to do this is to move this over to the other side to make it positive. So I go plus 4 force right hand side vertical in meters equals 110 kilonewtons per meter. So now I'm going to grab my calculator, if I can find it, because what I'm going to do is I'm going to divide through. So it's going to be my force vertical equals 110 kilonewtons per meter divided by 4 meters. And you'll see how these two will cancel out. I'm left with a force. By the looks of it, that force is going to be positive, which means it's going to be upwards. And let's go work this out. 110 divided by 4, 27.5 kilonewtons upwards. That's the force at my right hand side at the rotor joint. It is vertical. Confirming that it's upwards is because it's still positive. Okay. The next one is going to be, the next is to work out the force of the left hand side vertical and the force of the left hand side horizontal. So straight away, without even going anywhere, we can see by this picture, all the forces are normal forces. All normal forces, which are pointing straight down, perpendicular to the beam. There's no axial loads. There's straight down, straight up. That's a fixed point, so we can see there's none either. Therefore, there's no axial loads. Therefore, force left horizontal is 0. Please don't forget to state that. Because it is a pinpoint, it's a pinned or a fixed support, it has both vertical and horizontal. And then the next thing, so that's my horizontal. My force, the left-hand side vertical, will obviously be the forces downwards will equal the forces upwards. Pretty simple way to solve this, to go like that, equals all my forces upwards, so the sum of all my forces upwards. I've taken this to the other side, so it becomes a negative, all my forces downwards. Again, confirming my negative is downwards over there. I'm going to continue the calculation on this side. So all my forces upwards. Well, I'm going to have two forces upwards. I'm going to have my beam support, my rotor supports force, and of course the unknown, which is the force supporting this beam upwards, and my two forces downwards are going to be those two. So technically, I'm going to have all my forces upwards are going to be, what is that? Plus 27.5 kilonewtons plus whatever that force is. So those two forces force left hand vertical minus the two forces pointing down. I'm running out of space here in my calculations, so I'm going to do a bracket, so I'll move it there, and that will be 20 plus 30. So the sum of all the downward forces, those are kilonewtons. So technically what I have is (27.5) plus force LV minus 50. You guys get that? So I want to solve for that. I'll work those out together. (27.5) minus 50, negative 22.5 plus F left vertical. All I do is take that to that side there, and I've run out of space. me just tear this off for you. So I'll go back here and I'll just have 3 continued. 0 equals negative 22.5. It's still kilonewtons. I normally would add it in there. Now all I do is take that to the other side and it becomes positive 22.5 kilonewtons equals the force upwards. It's positive. Because it's positive, it confirms it's an upward force. So now I have got my force of my left, I've got my force of my right, I've got the force of those two, and now I can draw my simplified force diagram, which really is 20 kilonewtons, 30 kilonewtons. The force of my right is vertical, which is 27.5 kilonewtons. The force on my left vertical is 22.5 kilonewtons, and my horizontal force is effectively 0 kilonewtons. And that's my force diagram. How do I check to see it's correct? 20 plus 30 is 50 down. 27.5 plus 22, so we'll verify that. 27.5 plus 22.5 is 50. It's a balanced. I'll just double check that. So there we go. There is example number 2. It's a Lego man. Real simple process. Redraw the diagram. You'll slowly but surely get to just do the diagram being clockwise is positive, anti-clockwise or counterclockwise negative, and then your little square, and you've solved it there. And then we do, number 1 is that, drawing, assumptions, take a moment around the left-hand side or the fixed point, solve for that side, and then once you've done that one, we go and solve the other two. The force horizontal is 0, and the force there is vertical is that. That's it. Hope that helped.